everybody. Good morning. Myself, Dr. Shubhankar Sen, an associate professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the third lecture of Module 2 of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's lecture, we shall discuss the mesh generation using finite element methodology, and then we shall classify the structured and unstructured meshes with certain examples. Now, we shall elaborate on domain discretization and generation of nodes and elements. As we have already discussed that the finite element method is an improved version of the variational method, we identify the finite element method as a discretization technique. By discretization, we indicate that we discretize the governing equations, the boundary and initial conditions along with the domain. So this domain discretization, it is also known as mesh generation. The generation of mesh is consistent with the Eulerian approach used in fluid mechanics. The governing equations in fluid mechanics, they are written at points. Generation of mesh in FEM is consistent with Eulerian approach where we write the governing equations at points in space. Since FEM is a discretization technique, we split the domain into finite number of smaller non-overlapping unique subdomains and generate nodes where discretized equations are written. These nodes, they are actually spatial coordinates of selected points where we want the solutions of our unknown degrees of freedom. So, the finite element method being a discretization technique, generation of mesh or splitting of the domain into finite number of non-overlapping subdomains or elements is compulsory. Now, when we talk about the mesh generation, this can be done by algebraic method or by differential equation methods, and there are some other methods. Okay, so mesh generation we can now classify as generation can be done algebraically or via differential equation method. Now, we classify the meshes in 1 dimension and 2 dimension or multi dimensions as mesh in 1 dimension, in 2 dimensions 2D, or in 3 dimensions. We classify in 2 dimensions or 3 dimensions as structured and unstructured. When you go for structured, we can again classify them as Cartesian Then we can classify the second one as non-Cartesian, and the last one is curvilinear. Here I emphasize that when we generate the mesh, then distance between the nodal points, that must be a finite distance, that must be a perceptible distance. So distance between two nodal points cannot be infinitesimal or infinitely small. Now I make a small correction in spelling here. So this E came 2 times, and here one A should be there. Now let us discretize an arbitrary domain into finite elements. This is an arbitrary domain. This we denote as omega. Its boundary is capital gamma, and let us consider that the Poisson's equation is valid over this domain k del square t plus q equals to 0. So this is the continuum domain. Now this same domain we split using the subdomains or finite elements. There are many choices possible. So here we show one of the choices. The vertical lines and the horizontal lines that I am drawing here, these are known as the grid lines. So these are grid lines. We have vertical grid lines and then we have horizontal grid lines. The intersection of grid lines, they generate the nodal points where we solve for the unknown quantities. So these closed circles, these are the nodal points. The nodal points that are located at the boundary, these are the boundary nodal points at which we implement the boundary conditions. So in this case, we find that there are two families of grid lines, one family of vertical grid lines and other family of horizontal grid lines, and we say that the mesh which we are showing here is an example of a structured mesh where we can clearly discern the individual grid lines. So let us consider a representative element that I am highlighting here. This is a representative element that we denote by the symbol omega e, and its boundary is denoted by the symbol gamma e. Now the governing equation which is valid in the continuum level, this is not valid for the elements in the original form. The governing equation, when it is in the integral form or in the weighted integral form, that is valid for the individual elements. So this is the discretized domain. And this is a representative finite element domain where E is a finite element. Now the strong form k del square t plus q equals to 0 on omega, this is not valid on k del square t plus q equals to 0 on omega e. This second statement is not valid. So when we write the governing equation at the integral level, we have to use the integral form of the governing equation. So it should be written as integration over omega e, the weight function, and then the k del square t plus q d omega e equals to 0. This is the statement which is valid on omega e. So this we should take care of, that the original strong form, it is not valid in the discretized domain because the strong form this is the continuum equation. It is valid at the continuum level. When we discretize the domain, now instead of continuum, we have come to finiteness. So we have used discreteness in the problem, and then our original equation we have to cast in the weighted integral form, so that for every element the weighted integral statement is valid. Now the mesh which we have shown, this is the case of structured mesh, and then we can identify the total number of elements present in the mesh and total number of nodes present in the mesh. Total number of nodes in the mesh is given by the variable num np, and total number of elements in the mesh is given by the variable numl. These are integer quantities. If we consider a given finite element, for example, the case which we are showing here, the finite elements are of quadrilateral shape. We say these are bilinear quadrilaterals. These have 4 nodes. So these 4 nodes are identified as local nodes 1, 2, 3 and 4. We perform counterclockwise local node numbering. These local nodes are denoted by the symbol small a. So small a is the index for local node numbers. Now for this case, our a is varying from 1 to 4. For this present case, we have 4 local nodes. So these numbers is varying from 1 to 4. Now let us show the case of an unstructured mesh working on the same domain. So the domain which we have shown here, this domain we can now split into quadrilateral and triangular elements where there is no specific structure present. So let us first arbitrarily generate the mesh. We decompose the domain into finite number of non-overlapping subdomains or finite elements. So here we have discretized the domain, and we are now identifying the nodal points. So in this case, our elements, they are of quadrilateral shapes as well as they are of triangular shapes. So here some of the edges are curvilinear. Now if we look into this picture, this is an example of an unstructured mesh. So let us consider this is an arbitrary finite element omega e, and then its boundary is gamma e. So in this picture we cannot find the family of grid lines. It means that if we start from a node, now this line which we think as a grid line, it can go in this direction or it can go in this direction, or it can have many possibilities. It means that we cannot identify individual families of grid lines. So this is an example of an unstructured mesh in 2 dimensions composed of linear, triangular and bilinear quadrilateral elements. In this picture, the nodes which are located at the boundary, they are the boundary nodes, and the nodes which are inside, they are the internal nodes. So when we do the FEM formulation, at the beginning we identify the nodes which are located at the boundary and in which type of boundary condition will be applied on those nodes. So the set of essential boundary nodes, that is given by the symbol eta g. So eta g represents the set of EBC nodes. So the degree of freedom, it will be unknown in num p minus eta g nodes. DOF will be solved at num p minus eta g number of nodes. We have num p nodes, and then among these num p nodes, eta g nodes are located at the essential boundary. At the essential boundary, we know the solution. So other than the essential boundary, we may have natural boundary, we may have convective boundary, we may have radiative boundary. At all these boundaries, the degree of freedom is unknown. So at the non-Dirichlet boundaries and at the boundary nodes and at the internal nodes, we have to calculate the degree of freedom, or we have to generate the matrix equation system. The algebraic equations, those are written at the discrete nodal points. So here, these circles, I have already mentioned, these are the nodes and these are the arbitrary elements. Now, the total domain that is given, it can be thought of as composed of, as a union of the first element, then the second element, and then the third element up to the nth element, where n represents the null. The superscript e, it signifies the element, and omega 1e or omega ne represents the domain of a given element. And now the strong form, which was valid for omega, now in the weighted integral sense, it will be valid on the individual elements. It means that the strong form is valid on omega weighted integral statement is valid on omega e. So here we have given the basics of the mesh, that the variables in a mesh are number of nodal points, number of elements, then depending on which type of elements do we choose in one dimension or in multi dimensions, we choose the variable small a. For example, for the linear triangular elements which we have shown here, the small a, it varies from 1 to 3 for linear triangular elements, and it varies from 1 to 4 for bilinear quadrilateral elements. So now we shall illustrate the discretization procedure in one dimension. So mesh generation in one dimension. Here I mentioned that the word mesh is used in finite element method and finite volume method, whereas grid is used in finite difference method. Let us consider this picture. In finite difference method, we focus at the nodal points. So this intersection of the grid lines, these are known as the nodal points. So when we go for the finite difference method, our focus is only at the nodal points. So the space between the grid lines, that is not important in the finite difference method, and we use the terminology grid. Now for the same picture, when we go for the finite volume method or the finite element method, the space constructed by the grid lines, those are very important. We say that they are cells in finite volume or elements in finite element method. So we have nodes. Our discretization in finite volume or finite element methods, it starts from the cells, and then eventually we end up with the algebraic equations at the nodal points. It means that the space confined by the cell or the element is very important for the finite volume method or the finite element method. So when we use the word mesh in finite volume and finite element, we indicate that we are also emphasizing the importance of the space bounded by the nodal points grid lines. So cells or elements in FEM, cells in FVM or elements in FEM are important. Because of that, the first picture is known as grid. The second picture is known as mesh, even though their appearance is exactly same. Now, we go for the mesh generation in one dimension. So let us consider a bar of a given length. Let us take the length is 1 unit. We have to discretize this bar with certain number of finite elements. So when we start the discretization of the domain, we fix our coordinate system. We need a coordinate system reference, and then that is the starting of the domain discretization. We put the origin of the coordinate system. So this omega is given. We put the origin of the coordinate system at the left boundary, and this is our x-axis. Right boundary is x equals to 1. So this is x equals to 1. Now we select at the beginning how many nodes and how many elements do we want. So let us consider for this particular case we want 5 elements. So here I identify every element and every global node. So this distance between two successive nodes, this is known as the mesh size or grid size, which for the present example is 0.2. Then we say that this is global node 1, this is global node 2, this is global node 3, global node 4, global node 5, and global node 6. It means that we have 6 global nodes, and these numbers are unique numbers. So these numbers are denoted by the symbol capital A. We say that these are global node numbers. These are unique quantities. And here we have 5 elements. We identify the elements as 1, 2, 3, 4, and 5. So for this particular picture, we have NumNP, number of nodal points, equals to 6, and NumL, the number of elements in the mesh, equals to 5. So our element, it looks like a straight line segment containing 2 nodal points. So this is our mesh size or grid size. So this is the simplest possibility of a bar element. This element is known as a bar element with 2 nodes. So we say that this is linear or 2-noded bar element. It has 2 nodal points. These nodal points are identified by indices 1 and 2. These numbers 1 and 2, they are repetitive. They exist for every element. So these are local node numbers. Local nodes, they are denoted by the symbol small a. And this is an arbitrary element, small e. So this 1 and 2, these are local node numbers for these 2-noded bar elements. Now we have identified the elements and we have identified the global nodes. Then if we want to make the mesh for this particular case, we need the actual coordinates or the global coordinates of all these global nodes, and then we need a connectivity for every element and the global node and local node. It means that we need a correspondence of local node number and global node number, because the local node number is present in every element from 1 to 2, but we have global node numbers as unique numbers. So we need a correspondence between the local node number and the global node number. The correspondence between local or elemental and global node numbers is given by IEN array, which is expanded as identification element nodes. So we read it IEN small a small e equals to capital A. Now let us construct the IEN array for this example. So IEN AE equals to capital A. This is the definition. Now for this case, our A, it varies from 1 to 2. Our nummel represented by small e, it varies from 1 to 5. And numen P, it is indicated by capital A and it varies from 1 to 6. Now this IEN array is represented in a tabular form. In this table, there are two axes, one horizontal axis, that is the direction of the elements, and one vertical axis, that is the direction of the local node numbers. So we present it as IEN array as this is the axis for E and this is the axis for A. A is varying from 1 to 2 and E we have here 5 values 1, 2, 3, 4 and 5. So here we make this table for the first element, element 1. Our global nodes are 1 and 2. For local node corresponding to local node 1, this is the local node numbering. For element 1 corresponding to local node 1, global node number is 1. For same element corresponding to local node 2, where global node number is 2, so it is 1, 2. Now let us move to the second element. For the second element, first local node, the global node number is 2. And for the second local node, the global node number is 3. So now we can easily construct the IEN array for the third, fourth and fifth element. For the third element, these numbers are 3 and 4, I have written. For the fourth element, these are 4 and 5. And then for the last or the fifth element, these are 5 and 6. So this constructs the connectivity matrix or the IEN array for two noded bar elements using a very coarse mesh. When we say coarse mesh, we mean that we are using only a few number of elements and a few number of nodal points. Now, construction of IEN array is one part of mesh generation. It is still not complete. To construct the mesh and to plot the mesh, we need the information about the coordinates of every global node. So we need another array for storing the coordinates of individual global nodes. This array is known as the coordinate array, which we represent as the capital X array. So coordinate array or capital X array stores the global or actual coordinates of every global node. So the first thing is the IEN array and the second thing is the coordinate array. So in FEM mesh, we need first is IEN array or the connectivity array, and number 2 is the coordinate array. When we have this data, we can plot the data using a software and we can see the mesh where the nodes will be identified. Now it is defined as capital X R comma A equals to X bar. So capital X, this is the coordinate array, R is the range or dimensionality. A is the global node number and x bar is the coordinate vector. So x bar is the coordinate vector, R is the range or dimensionality, capital X is the coordinate array. Coordinate array. So now let us generate the coordinate array. So we have 6 nodes, node 1, 2, 3, 4, 5 and 6, global nodes 1, 2, 3, 4, 5, 6. This is x equals to 0, this is x equals to 1 and this is our x axis. So elements are 1, 2, 3, 4, 5 in one dimension. For this present case, our x array is x1 comma capital A equals to x bar. So this range or dimensionality, it varies from 1 to 3. In 1D, r equals to 1. So we can write it as, we can simplify it as an one-dimensional array instead of two-dimensional array as x of A equals to x bar. Okay, so in one dimension there is only x coordinate, y coordinate we don't have. So x bar equals to x in one dimension because y data is not available. Now let us consider the first global node. So the first global node coordinate is 0.0. The second global node, this is first global node, or capital A equals to 1. So this is the x coordinate. x2 equals to 0.0 plus delta x. Our delta x was 0.2, mesh size was 0.2. So this is 0.0 plus 0.2 equals to 0.2. So x3, it will be 0.4. We can easily understand it. Then for the fourth node, it is 0.6. For the fifth node, it is 0.8. And finally, for the sixth or the last node, our global coordinate is 1.0. Okay, so we have generated the IN array and we have generated the X array or the coordinate array. To plot the coordinate data, now we have to generate a file where we have to write the IN array and X array in a certain format. So the IN array data for the elements, we can write it 1, 2, 2, 3, 3, 4, 4, 5 and 5, 6. So here these are the IN data for the elements. This is for the first element, this is for the second element, this is for the third element, this is for the fourth element, and this is for the last element, the fifth element. Now for the first element we have written the global node numbers. So these quantities, they represent the global node numbers. So this is for local node 1 of element 1. So it means that the first data that we have written here, 1, 2, it is actually the global coordinates of local node 1 and local node 2 of element 1. Then we move for the next element, element 2. For element 2, the first local node, its global node numbering is capital A is 2. So this is 2. The next node is 3. For the third element, our numbers are 3 and 4. For the fourth element, our numbers are 4 and 5. And finally, for the fifth element, our numbers are fifth and sixth. So this is a presentation of the IN array data. Now we present the coordinate array. So here we have 6 coordinates. So the first coordinate is 0.0, the second coordinate is 0.2, the third coordinate is 0.4, the fourth coordinate is 0.6, the fifth coordinate is 0.8, and the last coordinate is 1.0. It means that this is x, or actual coordinate, of global node 1. Similarly, this is x coordinate of global node 2. It means that we need the global coordinate data of all the nodes and then the connectivity relationship. Then when we plot it, we can see it. Now, the difference with the finite difference and the finite volume method is that for finite difference method, we don't require any connectivity matrix. So in case of finite difference method, what we shall do, we can generate these 6 nodes. So we identify that this is the first node, we say I equals to 1, the second node, the third node, I equals to 3. Similarly, we can generate for the remaining nodes. So we have up to I equals to 6. Now we just write it as, if the grid size is delta x, x equals to 0.0 and x equals to 1.0, then we can write it, the coordinate array, as x1 equals to 0, x2 equals to 0.2, x3 equals to 0.4. So this is in finite difference. Then x4 equals to 0.6, x3 is 0.4, x4 is 0.6, x5 is 0.8, and finally x6 is 1.0. Okay, so these are the xi data, where I represents the nodal point. Now, when we write the data file using the finite difference method, we store it as I versus xi, the coordinate data. I is varying from 1 to 6. I is the index, it is an integer. I is the index of the node number. In finite difference, there is no concept of local node. Everything is global. Okay, so in finite difference, there is no weak form, there is no assembly. So here we have 6 values for I: 1, 2, 3, 4, 5, and 6. For 1, our coordinate is 0.0. For 2, it is 0.2. 3, it is 0.4. 4, it is 0.6. 5 is 0.8. And finally, the 6th global node is 1.0. So when we plot this data using, for example, text plot, we can easily get the finite difference mesh. Now, the same is valid for the finite volume mesh. For this case, in finite volume also, we don't need any connectivity matrix. So now we have illustrated the construction of finite element mesh and finite difference grid using the IN array and without using any connectivity relationship in finite difference. Now we can go for more examples in one dimension. So the bar which we have, it has 5 elements. So this is element 1, element 2, element 3, element 4, and element 5. For this, our element size was delta x, and the local nodes are 1 and 2. We say that this is 2-noded or linear bar element. So our global node numbers were 1, 2, 3, 4, 5, 6. Now for the same length of the domain and for the same number of elements, we have 5 elements. We can do the refinement of the element. We can use a higher order element. In a linear element, we have 2 nodes. In a quadratic element, we have 1 extra node at the middle. of the element. So we can think of the quadratic bar element for the same dimension. So it has one extra node at the middle of this element. We say this is the second node and this is the third node. So for this also, the mesh size is delta x. Now our global nodes, they will increase 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is our delta x. So this is element 1. This is element 2. This is element 3, element 4, and this is element 5 with size delta x. Okay. So delta x is the mesh size. So we can see that we are fixing null to 5, and then we are increasing the order, increase the number of nodes in each element, or use higher order bar elements. So for this case, our element is containing 3 local nodes and we have 11 global nodes. We have 5 elements, so this is the 3-noded or quadratic bar element. Now we can go to another case. This was case 1, this was case 2. Now we go for an even higher order element. So in that case, we keep the element number same. We use the same 5 elements to make the mesh. Now every element includes 2 more extra nodes. Previously for the quadratic element we had 1 extra node. Here we are taking 2 more extra nodes. So our elements are 1, 2, 3, 4 and 5. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. It means that when we go for quadratic to the cubic bar element, our total number of global node, it increases from 11 to 16. Here we show the element. It has 4 local nodes. Those nodes are equidistant, 1, 2, 3 and 4. So this is our mesh size delta x. So this is 4-noded or cubic bar element. If we generate the IEN array for this cubic bar element, then we can show it as IEN array for the cubic bar element, that is case 3. Our definition is IEN AE equals to capital A. So here E, here A is varying from 1 to 3 for this case. Our null equals to 5. Then E is varying from 1, 2, 3, 4, 5. For the first element, our nodes are 1, 2, 3, 4. So we have A is varying from 1 to 4. Let us make this chart first. For the first element, our nodes are 1, 2, 3, 4. For the second element, our nodes are 4, 5, 6, 7. For the third element, our nodes are 7, 8, 9, 10. For the fourth element, our nodes are 10, 11, 12, 13, and finally for the fifth element, our nodes are 13, 14, 15, and here 16. So this shows the construction of the mesh for one-dimensional bar elements of any order. So these elements that we have shown here, these are the examples of 1D bar elements. So the case 1 was for linear, case 2 was for quadratic, and case 3 was for cubic. There is a small correction here. X equals to 0 should be replaced by x equals to 1. In an one-dimensional mesh, if the mesh size is constant, then we say that the mesh is uniform, else the mesh is non-uniform. So in 1D, if delta x is constant, then the mesh is uniform. In one dimension, there is no concept of an unstructured mesh. When we talk about a structured and unstructured mesh, it indicates that we are talking in 2 dimensions or in 3 dimensions. So in multi-dimensions, in mesh generation, if we can identify grid lines within the mesh, then we say that we are using a structured mesh. If grid lines are not identifiable in a mesh, then we say that we are using an unstructured mesh. So in more details, in a structured mesh, we can identify families of grid lines such that a grid line from one family intersects the grid line from other family only once. Okay, so if distinct grid lines are not identifiable, then the mesh is unstructured. It indicates that in unstructured mesh, we don't identify a structure or a pattern. When we talk about structured and unstructured mesh, we talk about 2D or 3D problems. If we go for a structured mesh, we have already classified the structured meshes. So we have identified them as Cartesian, non-Cartesian, and curvilinear. Let us consider a square box in 2 dimensions with the edges parallel to the Cartesian axis. Then we generate the mesh. These are the XY axis. Then we generate the mesh for this problem. Here we can see that we have distinct families of grid lines. These vertical lines and the horizontal lines, these are known as the grid lines. So these are the grid lines. Now every grid line, it is either parallel to x-axis or parallel to y-axis. Here this is the mesh size, we say this is delta y, and here it is mesh size in x direction, this is delta x. So this is an example of a Cartesian mesh which is a structured mesh. So here we can identify 2 families of grid lines. One is horizontal family and other one is the vertical family. So in Cartesian structured mesh, we have a horizontal family of grid line and a vertical family of grid line. Let us go back to the sketch. So these are the horizontal grid lines. Now this vertical grid line, it intersects the horizontal grid line only one time. So every vertical grid line intersects every horizontal grid line at one time, and then these grid lines are parallel to the coordinates axis. Then you say that this is a Cartesian structured mesh. Now we give the example of non-Cartesian structured mesh. Here the same picture, if we get little modified for a parallelogram. So here we have a parallelogram. These are the XY axis. So here we are getting the grid lines. Now we have two families of grid lines. So this second family of grid line, this is the inclined family of grid line. Inclined family of grid lines. So we have two families of grid lines. Because of that, and every grid line from one family cuts the grid line from other family only one time, we have one horizontal family of grid lines. Then we can find that these grid lines, both of them are not aligned with the coordinate axis. The horizontal family of grid lines, they are parallel to the x-axis, but the inclined family of grid lines, that is not parallel to the y-axis, and because of that we say that this is not a Cartesian mesh. This is a non-Cartesian mesh made of straight grid lines. So grid lines are straight, because of that it is non-Cartesian grid lines. But if the grid lines are curvilinear, then we get the third case where polar grid is an example. Okay, so here we have horizontal grid lines. Now, for the first case, the Cartesian grid lines, we can use finite difference method, finite volume method, and finite element method directly. For the second case, where we are getting the non-Cartesian grid lines, we can use finite element method very easily. But for finite difference method, we need to perform coordinate transformation. For this case, finite volume method can be used without coordinate transformation for this case. Now, when we go for the curvilinear case, we can have one example of the polar grid. So here we can use finite element without coordinate transformation. So this is an example of a structured mesh where we are having two families of grid lines, the radial family of grid lines and the circumferential family of grid lines. So the tangential grid lines, they construct the circumferential family of grid lines. Circumferential family of grid lines and the radial family of grid lines. Here the grid lines are orthogonal. Now this is an example of polar grid. This mesh is known as a polar mesh. So we can write it as polar mesh. Now curvilinear structured mesh, we can give one more example here. So this is an example of curvilinear structured mesh where we have circumferential or tangential grid lines, circumferential grid lines, and these are the radial grid lines. Here I mentioned that the finite difference method does not work on the unstructured mesh. On unstructured mesh, we have to use either finite element method or the finite volume method. Now, we illustrate the construction of the structured mesh. So we consider the Cartesian structured mesh, which we have shown here. So let us consider the square. So we are taking as delta x equals to delta y. In my sketch, delta x is not looking like delta y. Let us take it that they are same. So this is delta x and this is delta y. Let us take that the square dimension is 3 units. In both the direction it is 3. So delta x equals to 1 and delta y equals to 1. So this coordinate is 3, 3 and the origin is 0, 0. Here we have 9 elements. So numL equals to 9 and we have 16 global nodes. So numNP equals to 16. Now the local element, we represent it here. This element is known as bilinear quadrilateral element. So it has 4 local nodes, 1, 2, 3 and 4. So we perform anti-clockwise or counterclockwise local node numbering. Now we identify the elements as 1, 2, 3, 4, 5, 6, 7, 8 and 9 and the global nodes as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and finally here it is 16. So the IEN array, it can be constructed here as IEN AE equals to capital A. So here our E is varying from 1 to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 and our local node numbers small a, it varies from 1 to 4. Then let us make this box. So here this first element, the global nodes are 1, 2, 6, 5. 1, 2, 6, 5. For the second element, the global nodes are 2, 3, 7, 6. 2, 3, 7, 6. For the third element, these numbers are 3, 4, 8, 7. 3, 4, 8, 7. For the fourth element, these are 5, 6, 10, 9. 5, 6, 10, 9. For the fifth element, these are 6, 7, 11, 10. 6, 7, 11, 10. For the sixth element, these are 7, 8, 12, 11. For the seventh element, these are 9, 10, 14, 13. For the eighth element, it is 10, 11, 15, 14 and finally for the last element it is 11, 12, 16, 15. So these are the capital A numbers, capital A quantities, the global node numbers, and during making this capital A values, we have made correspondence between the local node numbering here in this portion and the global node number in the original mesh. Now we have the coordinate array. So we have to generate the coordinate array here. Here as x, capital X, R, comma A equals to x bar, small x bar. So here R is 2, in 2D, R is 2. So we can write, for example, X array for X coordinate. R is 1 for X coordinate, R is 2 for Y coordinate. For the first global node, it is 0.0. X, y coordinate of the first global node, it is 0.0. So this is here 2 is for y coordinate. This 1 is global node. And this index 1 is for x coordinate. So like this, we can construct it as x 1 of, if we think of the fourth global node. So x coordinate is 3. And then for the same node, the y coordinate is 0.0. So similarly, for the 16th global node, our x coordinate is 3 and our y coordinate is 3, both. So like this, we can construct the coordinate array, and then we can present the coordinate array and the IN array in a data file, and we can get the mesh picture after plotting. So here, first we write the IN array here. The mesh data, it is represented as 1, 2, 6, 5, 2, 3, 7, 6, 3, 4, 8, 7, 5, 6, 10, 9. Then 6, 7, 11, 10. Then 7, 8, 12, 11. Then we have 9, 10, 14, 13, followed by 10, 11, 15, 14, and finally 11, 12, 16, 15. So the first one is for e equals to 1. The second data, global node number data for e equals to 2. This is for e equals to 3. This is for e equals to 4, e equals to 5, e equals to 6, element number 7, element number 8, element number 9. So this IN data, it is rearranged. This we have already shown for the one-dimensional problem. So here 1, 2, 6, 5 means the local node numbers correspondence and the global node number correspondence. These quantities are the capital A values. Capital A values. So local node 1, global node 1, local node 2, global node 2, local node 3, global node 6, local node 4, global node 5. So this is local node 4 for element 1. Here if we come, so this is global node 5. So this is the arrangement for the IN array. Now we can also construct the X array data. So if we consider the first coordinate, it is x 0.0, y 0.0. The second node, x is 1, delta x is 1, y is 1.0, y is 0.0. Third node, x is 2.0, y is 0.0. Fourth node, x is 3.0, y is 0.0. So this is a equals to 1, a equals to 2, a equals to 3, a equals to 4. So this is x coordinate. First data is for x coordinate. Second data is for the y coordinate. Now we go for the fifth node. For the fifth node, our delta x is 0, but our delta y is 1.0. So this is for a equals to 5. If we go for a equals to 6 next, then we get it is delta x is 1.0, and delta y is also 1.0. Then if we go for the 7th, then our delta x is 2.0 and delta y is 1.0. And then for the 8th node, it is 3.0 and 1.0. So here, like this, we can construct the remaining two rows of the coordinate array, and then we can get the FEM mesh complete. Now, this same mesh, if we use the finite difference method, so Cartesian structured mesh using finite difference method for the same mesh set, no, we don't need the connectivity array, or we don't need the IEN array using finite difference. So what we do here in finite difference, we identify the vertical lines as IH lines and the horizontal lines as J lines. So first line vertical stands for I equals to 1. This one is I equals to 2. This is I equals to 3. This one is I equals to 4. And here, this x-axis stands as j equals to 1. This is j equals to 2. This is j equals to 3. And then finally, this is j equals to 4. So that a node is identified by indices I and j in finite difference, where in finite element, we were using the indices capital A single index for the global node number. Now, when we plot the finite difference mesh, we require the data arranged in this manner: I, j, x, y. Here, I is varying from 1 to 4, j is varying from 1 to 4. So, this arrangement is required. So, if we consider the first vertical line, for example, so I equals to 1, then j will be 1, I will be 1, j will be 2, I will be 1, j will be 3, I will be 1, j will be 4. I equals to 1 means the first vertical grid line. Now, I equals to 1, j equals to 1 represents the origin for which x coordinate is 0.0, y coordinate is 0.0. I equals to 1, j equals to 2 for which x coordinate is 0. Actually, for this I equals to 1 case, all x coordinates are 0 and y coordinates will be incrementing in terms of delta y. So delta y is 1. So I1 j2, this will be 1.0 y coordinate. I1 j3, it will be 2.0, and I1 j4, this will be 3.0. Once this is done, then we move for I equals to 2. So next case is I equals to 2 and j is varying from 1 to 4. So the second vertical grid line. So when we go for the second vertical grid line, then our delta x is assigned to x values. This is constant. So this is delta x is 1.0. So all values are 1.0, 1.0, 1.0. And here the y coordinates are 0.0, 1.0, 2.0, and then 3.0. In this manner, we can go to I equals to 4 and we can get all the data in terms of I and j, and then we can construct the mesh. So this shows the formation of the Cartesian structured mesh. Now we show some examples using triangular elements. Now let us consider one example where we have the quadrilateral elements and the triangular elements. So let us consider this particular domain where we are using triangular element. So this is an example of unstructured mesh. Example of unstructured mesh. In this case, we don't identify families of grid lines to be present everywhere. We have one vertical family of grid lines clearly identifiable, one horizontal family of grid lines, but we have locally only one inclined grid line that is not present throughout the mesh. Because of that, we identify this as the unstructured mesh, where we cannot assign indices I, j, and k with every nodal point. So this is x coordinate, this is y coordinate. So this is our global node 1, element number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, these are our global nodes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now, already we have shown that for quadrilateral elements, our local node numbering follows this structure 1, 2, 3, 4 in the counterclockwise direction. Now we have triangular elements of two different orientations. So this is element E and this is also element E. So we again perform the counterclockwise node numbering. So here this is 1, 2, 3 and here this is 1, 2, 3 again. Both are following the counterclockwise local node numbering. Counterclockwise local node numbering convention. Now, if we construct the IEN array for this, again we write it IEN A E equals to capital A. Let us see that we have NAML number of elements equals to 10 and number of global nodes NAMIN P equals to 16. This is a hybrid mesh where we have two different types of elements, and this is a simple example of an unstructured mesh. So when we have this E, A, 1, 2, 3 and 4. So for triangular elements, A is varying from 1 to 3 and for the quadrilateral elements, A is varying from 1 to 4. Our elements are 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Then we make the IEN chart. For the first element, the global nodes are 1, 2, 6, 5. For the second element, these are 2, 3, 7, 6. For the third element, we have 3, 4, 8, 7. For the fourth element, we have 5, 6, 10, 9. For the fifth element, we have 6, 7, 11. For the sixth element, we have 6, 11, 10. For the seventh element, we have 7, 8, 12, 11. For the eighth element, we have 9, 10, 14, 13. For the ninth element, we have 10, 11, 15, 14. And finally, for the 10th element, we have 11, 12, 16, 15. In the previous example, we have already shown the construction of the X array. So for this unstructured mesh, we have the case of IEN data as well as the coordinate data. So we can easily construct the mesh by plotting it. So the coordinate array, it does not change with relative to the previous problem. Now, this particular case, this particular mesh, this is also an example of an unstructured mesh. This mesh is an example of an unstructured mesh. Finite difference method does not work on unstructured mesh, while finite element and finite volume methods do. Okay, now we show one example of mesh generation by using triangular elements. So let us consider this simple case of a rectangular geometry. So this is the case of a structured mesh. Structured mesh made of linear triangular elements. So triangular elements with 3 nodes, they are known as linear triangular elements. So we are given one rectangle. This we have discretized. This is omega. This we have discretized. And then we are having a numel equals to 8, 1, 2, 3, 4, 5, 6, 7, 8. And our global nodes are 1, 2, 3, 4, 5, 6, 7, 8, 9. So our num NP equals to 9. These triangular elements, we just do the local node numbering as 1, 2, 3. This is the eth element. And here also we have 1, 2, 3. This is the local node numbering for the eth element. Now we can construct the IEN array. So the IEN array for this case will be A is varying from 1 to 3 and E is varying from 1, 2, 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8. For the first element, our global node numbers are 1, 2, 4. For the second element, they are 2, 5, 4. 2, 5, 4. For the third element, it is 2, 3, 5. For the fourth element, it is 3, 6, 5. 3, 6, 5. For the fifth element, it is 4, 5, 7. For the sixth element, it is 5, 8, 7. For the seventh element, it is 5, 6, 8. And for the eighth element, it is 6, 9, 8. Now, we illustrate a simple case of multi-block mesh in structured mesh. Multi-block structured mesh. Let us consider the flow past a square cylinder, flow past a square object. Then we can show the construction of a very coarse mesh to study this. Now, this particular domain omega, we can split in multiple blocks. So one of the blocks will contain the object and remaining blocks, they will be just used for making coarse meshes. So here we show the problem as with 3 blocks. This is block 2, this is the object, then we have block 1, and then we have block 3. So here, in the next step, we make the mesh here. So this is the object. We make the mesh using bilinear quadrilateral elements. So here we have used quadrilateral elements to make the mesh. Now we shall do the numbering. Here our number of elements, let us first count. Element 1, element 2, element 3, element 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So in the first block, which is the I have identified as block 2, in block 2, here the number of elements it is 16. Then we go to block 1, numel. In block 1, there are 4 elements, so we identify them as after 16, we start from 16. So it is 17, 18, 19, 20. So we have completed the element numbering for blocks 1 and 2. In block 1, we have 4 elements. Now we shall move to the last block, the block 3. In block 3, we have again 4 elements. So the numbering will start after 20. So we have 21, 22, 23, and 24. So here we have total elements in the mesh equals to 16 plus 4 plus 4. We have total 24 elements in this mesh. Now we do the global node numbering. So the elements, the local node numbering for the elements, we perform it like this: 1, 2, 3, 4. For the global node numbering, we redraw the picture and show it again here. So here we have all the elements and nodes. Now we have our elements numbered as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. So the global node numbering starts from the top right corner of the cylinder of the object. Global node 1, global node 2, global node 3, global node 4, global node 5, global node 6, global node 7, global node 8, global node 9, global node 10, global node 11, global node 12, global node 13, global node 14, global node 15, global node 16, global node 17, global node 18, global node 19, global node 20, global node 21, global node 22, global node 23, global node 24, then global node 25, then global node 26, global node 27, global node 28, global node 29, global node 30, global node 31, global node 32, global node 33, global node 34, global node 35, and global node 36. So in this case, we have 36 global nodes. So that I mentioned in the previous page that total nodes equals to 36. Now we can calculate the coordinates. We have the IN array for each and every block. Now when we finalize the mesh, we have to arrange the data in the IN array for blocks 1, 2, and 3 in such a manner that at the common interface of blocks, this is the left interface between blocks 1 and 2, and this is the right interface between blocks 2 and 3, so that the global nodes have the same coordinate corresponding to the different elements and the different local node numbers. It means that, let us for example, this is the common node between element 8 and element 17. Now, element 8 belongs to block 2 and element 17 belongs to block 1. Now, this particular global node 12, it is the third local node of 17th element, whereas this is the fourth local node of the 8th element. So we have to assign the correspondence that third local node of element 17 represents the fourth local node of element 8. This correspondence, it should be defined for all the nodes which are located at the interface. Once it is done, we can generate the final mesh plot. So here, once we have the IN array, construct the IN array using the method which we have shown array, and also calculate the coordinate array. Once it is done, for elements located at the common interface, such as between blocks 1 and 2 and blocks 2 and 3, identify the common nodes so that a global node is uniquely defined. For example, the third local node of E equals to 17 in block 1 is also the fourth local node of E equals to 8 in block 2. So you should use conditions in your computer program so that this kind of overlapping, it can be identified. This overlapping you have to specify in your computer programming for all the nodes, the global nodes that are located at the common interfaces. So here we conclude today's discussion. We have shown mesh generation in one dimension using bar elements of linear and nonlinear types. We have shown generation of mesh data for FEM meshes in 2 dimensions. And finally, we highlighted the differences between structured and unstructured meshes. We have also shown the differences in finite difference and finite element methods in response to implementation for different types of meshes. For today's lecture, I recommend the textbooks by Farjigar and Perick as well as P.J.R. Hughes. Thank you very much for attending my lecture.